Okay, I thought I will lose more, but I lost only about 30%. I hope that you'll stick with me. Okay, today I will start, this is like a medium level lecture. I will talk about the Wald theorem, asymptotic formalism, Asimov dataset, Feldman-Cousins, proper likelihood, and CLS. And I won't stop till I finish. Okay, so, because there's no other way you can hear these things, so give me the chance, okay? I'll try to do my best. So yesterday we talked about the proper likelihood. So we had the test statistics. Alpha is the parameter of interest. Theta is the nuisance parameter. So lambda of alpha is the likelihood of alpha. Theta double hat is the maximum likelihood estimate of theta when you fix the parameter of interest to be the one you test, alpha, divided by the maximum likelihoods. Now Wilks tells us that this thing distributes like a chi-squared with n degrees of freedom, where n is the number of parameters of interest. Now since this is the maximum likelihood, this is always a fraction. The more incompatibility between the data and the tested hypothesis, the ratio will be smaller and the test statistics will be bigger, right? -2 log will be bigger. So today, my example, yesterday I gave a test case of spin. Today my test case will be bump hunting. So when we talk about bump hunting, we can either test the background-only hypothesis with the test statistics we call Q0. If we manage to reject H0, we have a discovery. Q0 is given simply by -2 log lambda evaluated at 0, so it's L of 0, theta double hat 0, divided by the maximum likelihood. If mu hat is greater than 0, and if there is downward fluctuation, we set the test statistic to 0. The reason is that we don't want downward fluctuation of the background to serve as an evidence against the background. For us, an evidence against the background is only if there is an upward fluctuation. We don't want to reject the standard model, right? Then, if I want to test the existence of the signal, test H mu, add some mass, I use the test statistics Q mu. If I reject the signal hypothesis, I actually exclude the Higgs with a mass mh, and then I derive an upper limit. The test statistics is given like -2 log of lambda evaluated at my tested hypothesis, mu, signal with strength mu. Again, upward fluctuation of the signal will not serve as an evidence against the signal. Because if I see too big a signal, then I don't want to reject it. This is fine with me. So here's some classification of possible test statistics. So if I want discovery of positive signal, I will use Q0. If I do a two-sided measurement, I will use P mu, just -2 log lambda. That's the classical test statistics. If I want to avoid negative signal because it makes no physics sense, I will use T tilde mu defined here, where if my measurement gives me something negative, I will use L of mu over L of 0 and not over L of mu hat. This is actually equivalent to the Feldman-Cousins test statistic, which I talked a little bit about yesterday and talk more today. To exclude a signal, I use Q mu. To exclude a signal and insisting that the signal is positive, I will use Q tilde mu. But these two are related. They are both, there's a monotonic relation between both of them. So actually, many times we prefer to use Q mu. It is much more convenient to deal with. So my test case is a bump hunt. Now, in order to make it realistic, like the gamma-gamma signal, what I did is something like this. Look. My signal has a narrow width with small mass and very wide with high mass. So it goes like, the width goes like m cubed. And I keep a signal of background ratio of 0.5%. This is very similar to the gamma-gamma. And I also wanted something that is dynamically changing. I didn't want a fixed signal resolution because I wanted you to be unable to do the classical Lucas, so like width over mass resolution, because mass resolution is not well defined when I have a varying width. You understand what I mean? The width of the signal is changing. So I can generate a gamma-gamma-like signal. The number of entries in the histogram is my luminosity. Is that okay? Please stop me if there's something you don't understand. So I'm going to talk about asymptotic approximation today, which was actually the method used and still being used by LHC. It was developed by Kyle Cranmer, Glenn Cowan, my student Ofer Vitells, and myself. This is actually a picture from last July when we celebrated 1,500 citations, and we had champagne in a machine learning workshop that we all were together. So the test statistics, let's, for simplicity, take the test statistics of TMU, but the conclusions will hold for anything that we'll do. So TMU is minus 2 log of lambda of mu. Lambda of mu is a test statistics testing the hypothesis H mu, L of mu, theta double hat mu, over L of mu hat theta hat. Again, higher values of TMU correspond to increasing incompatibility between the data and mu. So here is the theorem that does everything for us. It's called Wald theorem. It's from 1938, and it's the rediscovery of this theorem by Ofer, my student, that actually enabled us to solve the problem. What is the problem? Lambda of mu is L of mu over L of mu hat. Wilks tell us that the PDF of TMU is chi-square with 1 degree of freedom, which is fine. The problem is, how does TMU distribute under another hypothesis? Because we want to know what is the distribution of TMU under the signal hypothesis when we test the background hypothesis. This is the thing we want to know. And if we generate Monte Carlo, it might take us days, weeks, months, and years. So Wald came to our rescue, stating the following theorem, okay? If n is my sample size, take it to be the luminosity, then the test statistic TMU behave like a parabola, mu minus mu hat squared over sigma mu hat squared, plus O of 1 over square root of n, where mu hat distributes like a Gaussian around mu prime. And mu prime is the alternative hypothesis. If I test 0, mu prime can be 1. If I test 1, mu prime can be 0. Or if I test 0, mu prime can be any mu which is different than 0. So the problem is, how do we understand this, and how do we estimate sigma of mu hat? Sigma of mu hat is the real problem of this game here. We use the Asimov datasets, which I'll explain later, in order to estimate sigma. Here is an example when I test the background-only hypothesis, and my alternative hypothesis is mu prime equal 1, meaning that if I do lots of Monte Carlo experiment with a true value of 1 for mu prime, then mu hat will distribute like a Gaussian with an expectation value of 1. That's what I see here. Now, using this result of Wald, we could simply get every distribution that we wanted, including showing that f of t mu under mu prime, not under mu, follows what is called, and I'll show you the formula in a second, a non-central chi-square distribution with a non-centrality parameter lambda, which is mu minus mu prime squared over sigma squared. This is it. This is the formula. Now, you see immediately that if I check the distribution of t mu under mu, I should actually get back Wilks' theorem. So if indeed I set mu prime to be mu, the non-centrality parameter becomes 0, and you simply get a chi-square. This is a chi-square. F of t mu is 1 over square root of 2 pi t mu e to the minus half t mu. This is a chi-square. So Wald becomes Wilks when you check the distribution of t mu under the same hypothesis that you check under mu. H0 under 0, T0 under 0 is a chi-square, T1 under 1 is a chi-square. This is an example of two LHC-like experiments that we do with our toy model with the bump. And now to show you, understanding Wald will help you to understand everything. So I spend a little bit time on it because I think it's important. I want to show you what it means. Here's a demonstration of Wald theorem. We use a luminosity of 60,000 entries here, and let them distribute under this. We want to check that minus 2 log lambda of mu really distributes like this. So we test the background only hypothesis, and it's supposed to, according to Wald, look at this thing. If I test if mu equals 0, then minus 2 log lambda of 0 is mu hat squared over sigma of mu hat squared for mu hat greater than 0, and 0 for downward fluctuation of the background for mu hat less than 0. Now I generate events around 0, and I generate events around 1. When I generate around 1, around the alternative, so you see what happens, I really get a parabola. This is Q0. When I generate events around 0, so if mu hat is greater than 0, it indeed goes like this. You see the blue one here. If mu hat is less than 0, the result of the test statistics are really below here, and it all fits the parabola that we are interested in. Now let's do the other way around. Let's test the signal hypothesis. So when I test the signal hypothesis, I look at Q1. Q1, of course, is a function of the data. So minus 2 log lambda of 1 will be, according to this, 1 minus mu hat squared over sigma mu hat squared if mu hat is less than 1. And if mu hat is greater than 1, upward fluctuation of the signal do not serve as evidence against the signal. It should be 0. And now I do this thing. If I generate event with alternative mu hat around mu prime equals 0, it acts beautifully like a parabola. That's the blue things here. If I generate events around mu hat equal 1, when mu prime is 1, then I get, if mu hat is greater than 1, is 0. And if mu hat is less than 1, I get a parabola. So Wald works perfectly. Now it takes time to digest Wald, but everything is in Wald. So to finally test Wald theorem, what we did is check how the relative error of Q0 minus the prediction of Wald divided by Q0 behave as a function of the luminosity. And indeed we see that Wald works. Luminosity is the number of entries in the histogram. And we see that as we increase the luminosity, this relative error decreases and decreases and decreases until for infinite luminosity we'll get that the Wald approximation is an identity. So we are left with the problem of how to determine sigma, and the answer is with the dataset we call Asimov dataset, and I will talk about it in a second. So I wish I could just stop the lecture here for a day so you digest it and you come back tomorrow, because this is everything you need to know. Once you know this, you can derive everything. So all you have to do is to dig papers from 1930s and in statistics, rediscover them in physics, and you can do miracles. It happened more than once to me, and it happened to friends, and all you have to do is rediscover statistics. I mean, the statisticians don't bother about these things because for them this is old news, and for us it's new news. So with Wilks, we know this distribution of f of q null under h null, and with Wald, we can calculate this distribution of q null under h alt. This is the only thing that you want. if you know these two distributions, you don't need to generate even one Monte Carlo experiment. And this is fantastic. So if I have the asymptotics, Wald gives me the asymptotic because it gives me a way to calculate the behavior of f of h null under h alt. And this is what I want. So I can actually have a second look at the Niemann construction and go to Feldman-Cousins. We're bothered by the following things. They're bothered by something called flip-flopping. When we do an experiment and we don't observe enough fluctuations, that tells a story, then we say, there's no signal here, let's do a limit. And if we suddenly see a huge fluctuation, we say, no limit, let's do a measurement, here we have a signal, let's measure the cross-section. So to flip our intention, flip what we are doing from setting a limit to a measurement based on what we see. And we don't decide in advance what we do because we don't know what will be the result of the experiment. So they claim that if you use such a test statistic that is flip-flopping between a limit and a measurement, you actually lose the property of the coverage. Your confidence level is not true because you don't really take it. When you report a limit, you should also include in your ensemble of possible results that if you would have had a fluctuation, you would make a measurement. So this increases your space, and your coverage actually is not the confidence level that you report. This is nice, except that in my mind, it's no problem for physicists. Come on. You know what we do in LHC these days. Even we started it actually already in the discovery. We report two things. Look at the discovery paper, you'll see they're both. You see they're both the limit and the p-value of the discovery. And since then, it's true that if you see nothing, you'll produce a limit because it's ridiculous to produce a measurement here. But when things make sense, we produce both of them when we are not sure and we don't know. So I don't see a problem with this, but it bothered Bob Cousins and Gary Feldman a lot. So they decided that maybe we let the data decide for us, let the data, the observation decide for us objectively, not based on our feeling, if we do a limit or a two-sided measurement. Already yesterday we saw that they didn't invent anything because it exists already in the Niemann construction. It's built into the Niemann construction. I showed you this one observation gave us, using the belt, gave us a measurement, and somebody asked me what happens if the observation occurs, you asked me I think, what happens if the observation occurs right at the zero when the signal, possible signal, true signal is zero? And the answer was that then you set a limit. So this is actually what Feldman and Cousins did. They introduced the flip-flop and they brought back to life, like we did with the Wald, they brought back to life the Niemann construction, but with a specific purpose to let the data decide for us if we have a limit or a two-sided interval, and do it in a way which preserves, by construction, the coverage. So the test statistics they were using is actually the profile likelihood. They did not allow negative signals. So when S hat was less than 0, like our mu hat, right? When S hat was less than 0, you use the likelihood of S plus B over likelihood of B instead of likelihood of S hat plus B. And this is the result they got. When they build a confidence belt, if the observation occurs here, they have a two-sided interval in the true parameters value. This is the measured parameters value. And this is the space, the measured parameter space, and this is the true parameters space. So you make a measurement, and the measurement is in the measured, in the estimator's parameter space, and you deduce something by inversion in the true parameter space. So if the observation is here, you deduce a two-sided, and if the observation is here, you deduce an upper limit, because the signal cannot be less than 0. So the signal must be less than whatever value we get here. Now I will show you how you can get more insight into Feldman-Cousins using the asymptotics. So we use the test statistics which allows only positive signal, which is called T tilde mu. And we use Wald actually to tell us what is the distribution of the test statistic, because once we have Wald, we know how to do it. Now, I'm not going to read for you all these formulas because it's crazy. But what I want you to internalize here is the fact that using the asymptotics, I have everything in hand. Because I have, for example, P mu is 1 minus the cumulative distribution f of T tilde mu mu, which is given here. The cumulative distribution is the area. And you always have to remember that you don't see it here, but the value of the test statistic depends on mu hat. Right? The value of the test statistics depends on what is the observation. It's hidden. You don't see it here, but it's there. So what we are interested to know is what is the confidence interval of mu. Mu is a true parameter space at the 95% confidence level, meaning mu, all mu that actually satisfy p-value greater or equal 5%. So using the asymptotics, first of all, let's generate it just to get a feeling. If I take, for example, mu equal 0.3, mu true equal 0.3 and sigma 0.2, and I generate the Wald, I get that everything, all the results lie between chi-square with 1 degree of freedom and half a chi-square with 1 degree of freedom. For example, if my truth mu is 1, I get a chi-square with 1 degree of freedom, and if my truth mu is 0, I get half a chi-square with 1 degree of freedom. But this shouldn't surprise you, because if you will look carefully at the table of possible test statistics that I gave you, and you compare T tilde 0 with Q0, you will surprisingly discover that they are identical. So Q0, our test statistics to test background and make a discovery, is identical to T tilde 0. And that's why it distributes like chi-square with, well, like half a chi-square with 1 degree of freedom. Now here's the thing. I can use the asymptotic, set mu true to be some fixed value, say 0.2. Now P mu, as I told you, is a function of the data, of mu hat, because the T tilde mu is a function of mu hat. So P mu of mu hat is 1 minus the cumulative f of T tilde mu of mu hat given mu. And this gives me a dependence between P mu and mu hat, which looks like this. The peak is exactly the true value at 0.2. And if I want to build a confidence interval in the mu hat, in the measurement space, all I have to do is to look at all the mu hat where P mu is greater than 5%. So it's this thing here. Then using the asymptotic, I can also plot T tilde mu as a function of mu hat, because T tilde mu is a function of mu hat, and this is exactly Wald. The parabola is a Wald. So I can see that my interval for mu hat here, given mu true equal 0.2, my interval for mu hat is given here. And it occurs at T tilde mu equal 3.31. Now I can repeat it for each truth mu. I repeat it, and I get the belt, right? I play this mu, and I get this, For example, in this example, mu true is 0.2, that's the previous example. And I see that my interval in mu hat is given here. I generate here a Gaussian around 0.2, this is Wald, 0.2. And the areas which are not included in the 95%, the 5% are this green area and orange area. Now let's take an extreme case where mu true is close to 0. Something strange is happening here. When mu true is close to 0, what happens when I construct the interval in mu hat? It actually goes from some value here all the way almost to infinite here. It's like one-sided. And that's how I get the structure of the belt to look like this. I can show you, demonstrate to you what we claimed already when I demonstrated the Niemann construction. The values of mu true, for which p mu is 5%, for a given mu hat, for example, mu hat is 0.5. These values here, the inversion of mu hat to mu true, are actually my confidence interval. And I show it by plotting mu true as a function of p mu, because I have the formulas. I get this thing which should be familiar to you. And I actually invert the interval in mu hat into the interval in mu true, given my observation, and I get exactly the same interval as I should expect. I know it's hard to follow it so quickly, but the slides are there and you can look. By the way, the slides are already there, so if somebody doesn't see well the board, just open the slides. So now I see that using the asymptotics, I easily constructed the Niemann construction of the Feldman-Cousins easily, and I can see immediately that for some measurements, depends on the measurement, I will get a two-sided, and from some measurement, I will get a limit, a one-sided. So I let the data decide for me what type of interval I get, two-sided or one-sided. The data decides for me, and actually I get, by construction, a coverage as long as the asymptotics holds. But here's another observation that you get from the asymptotics that makes your life ultra easy. Remember that when I plot t tilde mu as a function of mu hat, I showed it to you here, where was it? I get at some value of t tilde mu in which I get actually the interval. Here it was 3.31. So when one played the game, one sees that as I actually increase mu true, the value of mu true goes away from 0. Very quickly, already for 0.5, I get the t tilde mu is 3.841. I go to 1, it's already 3.841. So I can now do an approximation. I can build a bet simply by taking actually the interval that is given by 3.84. So now you see, this interval is not identical to the one that I will do if I do the full construction, but the confidence interval you get here will always be with a higher confidence level than the 95% in this example. So you are, in a way, conservative. So if you want to do a quick job, all you have to do is substitute t tilde mu equal 3.84, build your belt, and this is it. It was just a side comment that we noticed. Okay. Now I move to discuss Q0 for discovery. So Q0, as I told you, is identical, equivalent to t tilde 0, minus 2 log lambda of mu hat greater equals 0. And if there are downward fluctuation, I actually set Q0 to be 0 because I don't want downward fluctuation to serve as an evidence against the background. So what does Wald tell us in case of T0? First of all, using Wald, we get the formula of f of Q0. What is the distribution, PDF of Q0 under some hypothesis mu prime, which can be 0, then it will be Wilks, so it's this thing here. It's half a delta because of all the cases in which mu, when you generate background-only experiment, half of the cases mu hat greater than 0, and half the cases mu hat less than 0. When mu hat is negative, I get a delta function because I set the test statistics to be 0. So it's a delta function with a height of 0.5 here, and the rest is simply a Kaiser with 1 degree of freedom. Now, in order to get the approximation for this distribution of Q0 under the alternative hypothesis, where mu prime is not mu or, say, 1, then I get the formula here. You see, first of all, that it agrees very well. And here is So this is Wald. Now I want also to show you something else in case you don't know. I forgot to show it before. That I can easily show you that if you know Q0 or Q0 observer, whatever, you have some data set and you calculate the test statistics for this data set, by taking the square root of this, you get the significance of the fluctuation, the z. This is proven here. F of Q00 is just a cumulative distribution for minus infinite to the observed Q0 of the distribution. This is what we call phi of square root of Q0 based on Wald. P0, if I have an observation here, so P0 is all the area. So it's 1 minus this. So it's the area when you are away from the null hypothesis in this direction. Then Z0 is given by phi minus 1, the inverse of 1 minus P0, which turns out to be simply square root of Q0. So you remember, if Q0 is 25, your observation is 5 sigma. Q0 is 16, your observation is 4 sigma. If your Q0 observed is 9, your observation is 3 sigma. If it's less than 1, you observe nothing. So that's the way it works. The next thing you want to know is you want to ask your financing agency for money. Why? Because you want to discover a Z prime. Because we already discovered the Higgs, you want to discover a Z prime. Now you know that the approximate plane of the future circular collider or whatever it is, because you are very young, so that's the things you would probably work on. And they ask you, okay, this is how much do you think that the FCC should work at which energy in order for you to get a 3 sigma observation for the signal? How do you answer this question? So the way to answer this question is actually to say, if I increase the luminosity, the separation between the background hypothesis and the alternative hypothesis will be better, right? This is intuitive. I will show it to you in a second, but this is intuitive. So the idea is to assume some luminosity for your future circular collider, some luminosity, run Monte Carlo with this luminosity, inject the signal you want to discover or exclude, whatever, inject the signal you want to exclude first, generate these things here. Each one gives you a possible significance for discovery. This is a 3 sigma here, this is a 2 sigma, this is a 5 sigma, 25, yeah? And then you take the median significance, or average or median significance, and you tell them, okay, I cannot tell you it all fluctuates, but on the average or the median of my measurements will give me, I have a sensitivity to get a 3 sigma, whatever. So what you want is the median of this distribution, and it gives you your expected sensitivity. In this case, 3 sigma. Okay? That's what you want. So option 1 to answer it will be to toss 1,000,000 background-only events. That's your null hypothesis. And you get the background PDF, but that we know already. It should be Kaiser with 1 degree of freedom. We know it already. Then you have to toss another 1 billion signal plus background events to get this distribution. Find the significance for each one of them, then find the median significance. We started to play these games, and it simply lasted for ages. I'm talking about sometimes you go to your student. In my age, you go to your student. You don't do it, okay? And you tell him what's going on now. It's only 10%. I mean, we need another 3, 4 days, 5 days, sometimes a week, and sometimes, it's crashed during the night. I have to start it all over again. So this is one way to go. Another way to go is to use, if you know this formula, then it's easy for you to calculate the median. And actually, we found out that you can do it in a fraction of a second. Simply, this median This median is a result of some data set. And this data set happens to be a very special data set. We call it the Asimov data set, which gives you immediately the median. Why do we call it the Asimov data set? Because of a story by Asimov. The story tells you that in the future, you will use an electronic election system, and instead of sending people to vote or even vote for home, the big brother knows every one of you, each and every one of you. He knows its political tendencies, etc., etc. So why not, since I know all of you, I can choose the person with the kind of the average ideas or whatever, put him in front of a computer and tell me how much Trump gets, how much Hillary gets, how much this gets, and now tell me how many senators this state gets, how many senators this gets. And this is it. When he finishes, I use this representative person as a representative of the population. I will get the average of the population. I will get the vote of the population. So this reference voter is the Asimov data set. We use a single representative individual to stand in for the entire population. And this will help us to evaluate the sensitivity of a statistical method. So an ensemble of simulated experiments with alternative hypotheses can be simply replaced by a single representative one. And this is called the Asimov dataset. The Asimov dataset immediately delivers the desired median sensitivity. So one is exempted from performing lots of Monte Carlo experiments, time-consuming. And the surprise is that it's a trivial dataset. The Asimov dataset is trivially constructed from the true parameters value. For example, if you want to know, if you test the Bernoulli hypothesis and you want to know your sensitivity for some signal given by S is a cross-section times luminosity times acceptance times efficiency, you simply construct an Asimov data test NA, and Asimov equals S plus B, the sum of your expectation for background and signal. Or if you want to test your signal hypothesis, your alternative hypothesis is the background only, simply take the data set which is made of the background only. Now, of course, the expectation is not necessarily an integer, okay? When you calculate luminosity times cross-section, you might get it, you expect 3.75 events. So the Asimov data set can be a fractional number, even though I call it NA. And you don't have a problem with it because you use likelihood ratios, so the factorials cancel out. So it's easy to calculate. So here's an example, okay? Here is my bump with the luminosity of 1000. This is the Asimov data set here. And behind it, you don't see it, also the median is plotted. So they are simply identical. Or, for example, something less trivial. What is the distribution of the P0s, P0, under the alternative hypothesis, H1? The median is here. And if you look very carefully, you see there are two lines here. There's a red one and a blue one behind. One is done by really performing the toys and look at the median, and one is done by simply plugging in the Asimov dataset. So it works fantastic. Here's another example. You see, the Asimov dataset is Q0 Asimov. So you set mu hat to be 1 because this is the background only, under background only, FQ0 under 0, and this is FQ0 under 1. Q0 Asimov is given by setting the alternative hypothesis to your expected true value. So mu hat is 1. And you actually use it as at 125 because this is our example plus B. And you see that they simply lie one on top of each other. So it works. And now comes a real thing that really makes your life very, very easy. In order to get the asymptotics, you need to know what is the sigma of mu hat that you should actually plug into this Wald formula. Now, this sigma depends on the tested hypothesis, on mu. I cannot make it even more clear. Sigma of mu hat of the measurement depends on the tested hypothesis mu. You test a different mu, sigma changes. And it's intuitive, because think about it. If the background, if the signal is very, very small, then S plus B is very equal to B, so you cannot separate between S plus B and B, so you expect the sigma to be big. And if the signal is huge, it's very easy to separate them, so sigma will be small. So sigma depends on mu. So for the Asimov dataset, by definition, mu hat is simply mu true, because that's what I substitute. So for the specific Asimov dataset, the sigma is not dependent on mu hat, it depends on mu. Mu hat distributes like a parabola, but the sigma of the parabola depends on the tested hypothesis. So Q mu Asimov is minus 2 log lambda Asimov of mu, which is simply mu minus mu true squared over sigma mu hat squared. Well, there's no approximation here, because that's by definition the way Asimov works. When I have this, I immediately can get from here sigma mu hat squared is mu minus mu true squared over q mu Asimov, where mu hat median or average is mu true. If I test mu equals 0, the alternative mu true is 1, so sigma squared is 1 over q0 Asimov. If I test mu equal 1, then I want to know the distribution under the alternative, mu true equals 0. I get sigma squared mu is 1 over q1 Asimov. Because now mu true is 0, and this is what you get, and mu is 1. In general, if I test for exclusion, mu true of the alternative is 0, and sigma mu hat squared is mu squared over q mu Asimov. This is a very, very powerful result. I want to demonstrate it to you. So here, I play my game, and what I do is with my toy model, I actually change the luminosity from 1,000 to 40,000. I get my mu hat distribution, and I fit it with the Gaussian, with the width of the Gaussian given by 1 over q1 Asimov. And I see that it works fantastically. And actually, I can even calculate the behavior of sigma mu hat as a function of the luminosity. If I increase the luminosity, the resolution becomes better. I can separate the hypothesis better, and I get actually the behavior of sigma mu hat, which goes below, down, 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 and shrinks and shrinks and shrinks as the luminosity goes higher. Yeah, we are doing very well. We will finish just a little bit after time, but we started at 11:10, I think, so there's no problem. So here is an example of a data set. And in order to quantify the fluctuations that I see, I simply calculate the p-value as a function of the mass. P-value quantify how many sigmas is the fluctuation, right? This function phi minus 1 of 1 minus p gives you the significance. So I just want to show you that even though I generate background only experiment here, actually, no, we generated here signal plus background. We generated a signal at 125 plus background. You might just get, by chance, fluctuations anywhere in the mass range, but this is something we'll talk about tomorrow, because this is the look elsewhere effect. Now, at each place, the dashed line here is what would a typical signal look like, the p-value typical signal, when I plug in the Asimov data set, which is exactly the expected signal at 125 plus b. So I would have expected to see this behavior here. Now, if I generate signals as background event, this might fluctuate, okay, up or down. If it fluctuates up, I mean more signal, then the p-value is smaller. It's going to go away from the null hypothesis with the background only. Now, to quantify how much away I am from the expectation, I look at the signal strength, which is my sigma observed over sigma expected. If I get exactly what I expect, this thing will be 1. Now, here I see something strange. If there was a signal at 110, this would have been exactly what I would have expected. So I would go to the press and say I might have a signal here if the significance was high enough. This is a 3 sigma. This is calling for the press. But this is very, very confusing because we also see here a signal at 125 with a strength which is much more than 1. Like actually we observe that, and let's see. This is a toy model, I remind you. So many things can happen. This time I won't stop it to show you because it will take me time, but you understand that that you can get crazy, you can see crazy fluctuations that happen here. Crazy. We'll dig it more tomorrow when we will look at the Lucas effect, that crazy things might happen. Okay, so indeed, this is an example from real life. The discovery of the Higgs, this is from gamma gamma, which is really similar to what I was doing with the toy model. We see a fluctuation at a level of about, I don't know what is 4 sigma, 4 point something sigma. This is what we see, and the expectation is given here. So the signal we observed at this point of time that I looked at, it's not an official plot, I took it just from my logbook. But this fluctuation at that time was about, the mu was 1.3 or something crazy, okay? But this is life. Okay, next I'm going to discuss about how you do exclusion. So your test statistic is Q mu, which is minus 2 log lambda mu when mu hat is less equal mu, and 0 for mu hat greater than mu, meaning upward fluctuation of the signal will not serve as an evidence against the signal. So again, I can use Wald to get the distribution of FQ mu under mu. This is the Wilks theorem. It's half a chi-square. The half comes from all the cases when I generate events around mu hat equal mu, half of the time I'll be more than mu. Then I'll get a delta function, and half of the time I'll be less than mu, and then I'll get a chi-square with 1 degree of freedom. And using Wald, I can also calculate what would be f of q mu under 0. F of q1 under 0 is this thing here. And the asymptotic works great, and this is the Asimov or the median. Both are plotted here, you can't even tell one from the other. This is the proof that the Asimov and the median actually coincide. So what we want to do is to test the hypothesis h mu, this one, by calculate this p-value. Normally, we would have said that if this p-value is less equal 5%, I reject the h mu hypothesis. So here is some formulation. Here I look at a log scale. Let null hypothesis is h mu. An alternative hypothesis is with the expectation of mu hat equals 0. So there is a significance for the alternative hypothesis observation, which is square root of q mu. Here I can calculate q mu Asimov and get the sigma mu equal mu over square root of q mu Asimov. We already derived it. Now I can calculate p mu equals 1 minus phi of square root of q mu. Let's call it alpha, normally 5%. So square root of q mu is phi minus 1 of 1 minus alpha. Using Wald, we have mu minus mu hat over sigma is phi minus 1, 1 minus alpha. mu up will be all the mu that satisfies that p mu is less equal 5%. So from this, I open this, and I get mu up is mu hat plus sigma mu hat at, evaluated at mu up, phi minus 1 of 1 minus 0.05 if I'm looking for 95% confidence level. So it simply becomes mu hat plus sigma mu hat at mu up times 1.64. I bet my life that nobody managed to follow me here. But it doesn't matter. It's there. It's there, and it's not so well described in the paper in so detailed, so you can always look at this and get it, okay? So now in order to make things clear to you, I want to show you some other thing, okay? How do I find the expected mu up? You design an experiment because this is what you'll do a lot. Unfortunately, this is what you'll do a lot. You're very young here. You'll write a lot of proposals, and you will be asked by first your supervisor, and then you will ask your students. In the middle, you will do it yourself, but that will be a very short time that you'll do it yourself. Now you do what your supervisor tells you, then you'll tell your student what to do. In the middle, you'll do things yourself. So scan mu, find q mu median, which is median of f of q mu under 0. Mu up will be all the mu where the area here under the null hypothesis is 5%. So this is calculated by this integral here, which is the area here. Asimov tells us that the expectation, for the expectation, the alternative has mu hat equals 0. So mu up is simply sigma mu hat at mu up times 1.64. It's trivial to do it. But the problem is that look what happens here. I have mu up here, and I have sigma of mu hat depends on mu up here. How do I solve these two things? So the way to solve it is numerically. Mu equal mu up is this line here, and 1.64 sigma of mu up is 1.64 mu up over square root of mu up Asimov. This is the sigma as we derived before. Gives me this thing which hardly changes. It's a little bit slope here. And when they coincide, this gives you your mu up, which is 0.47. So this is the way to solve it. That's the easiest way to solve it, not analytically, but by doing this thing here. The thing here is that if you want to know how tolerate you are with the mu up, you tell the funding agency, I got that with this luminosity in this machine, my sensitivity is to get an upper limit on the signal of say 0.5. So they tell you, yeah, but what is the uncertainty on this mu up that you give? So you tell them, for this I will generate lots of experiments. In each one of them I will put the mu up. So I will get some distribution. I will look where 68% of the mu up falls. This is my band, uncertainty band for mu up. I can also look for 2 sigma. This is the yellow band. So I have an uncertainty band on mu up, and this tells me how well, how sensitive I am, how good is my experiment, okay? So, of course, you understand that easily with the Asimov, I don't have to do all these experiments. Asimov can tell me exactly where the yellow and the green bands fall. It's given by sigma of mu hat, evaluated at mu up plus 1 sigma or 2 sigma is given by this value here. And I can calculate using the Asimov the bands. And I can actually do it for every mass. And suddenly you get a very familiar plot, the Brazil plot. The Brazil plot tells you what is my expectation for the exclusion. This is how good the experiment. And this is where you measure which one is doing better, Atlas or CMS, not by observation, which might be unlucky or lucky. If you know which analysis is designed better, you look at the median and its bands. And then you look at the observation and you get some observed mu up. Now, since we have a signal at 125, we cannot exclude this region here. And that's what happened in real life. This is real life. You see that what happened to us in real life, that we couldn't we started by excluding everything, but there was no way we could exclude the 125 because there was a signal there. So you cannot exclude where there is a signal. So you see that all the results that we get for exclusion are within the 1 sigma band here, the green band, but the observation to 125 is at least 1, 2, 3, 4, 5, 4 sigma away from the expectation. So later you can look at this and see how you actually, what is the meaning. Now you will understand easily what is the meaning. In 2010, I spent some time with the xenon experiment. Now, this was the beginning of the, it's been, I don't know, 15 years or something that we really do astroparticle physics. Most of the physicists doing it were, not anymore, were coming from high energy physics, from particle physics. So I spent some time with xenon, some friends brought me, and then I said, in astrophysics, they always do Bayesian physics. I said, why don't you do what we do with the Higgs? This is much more illuminating by looking at your expectation and your observed and compare the observation with expectation, you can get a lot of illumination of what's going on there. And now if you look at all the plots of lux of xenon, you will see these plots which will remind you very much the Higgs. That's because I simply brought it from Atlas to xenon in 2010. So you can do these things not only in high energy physics, but also in astroparticle physics. And this was a real field changer because they were doing all the time Bayesian, and now they do frequentist. The last subject for today is looking again at the CLS. You remember from yesterday, I showed you that Birnbaum, already in 1962, claimed that if when you exclude the tested hypothesis in favor of the alternative hypothesis, most of the time the alternative hypothesis is simply wrong, you didn't do anything. It's no good. So the real measure of how good your exclusion is to take the significance divided by the power. Or P prime U is P mu over 1 minus P0. This is called the CLS method, and it was Alex Reed who brought it to the community in 2002 in this paper given here. And then Birnbaum was rediscovered later by Ofer, my student Ofer Vitells, rediscovered Birnbaum, and then Alex and Ofer together wrote the entry for, I think, for Wikipedia, for CLS. So you'll see the very nice article in Wikipedia about CLS. That's why I told you that I know some experts who wrote in the Wikipedia the statistical literature. So let me show you here some examples. How the CLS looks like when we use the profile likelihood. So I have here, this is Q mu under mu. So it's half a chi-square. This is Q mu under 1. So it looks like this. This is the Asimov data set. And it tells us that this green area is your expectation. P1 expected is 1.7%. This is fantastic. This analysis is fantastic. Luminosity is fantastic. Everything is great. But be careful, because you have to divide this p-value by the power, which is this area here, the power. And the power here is 68%. This is expectation. Sorry. This is expectation. This is the Asimov. So by definition, if this is the Asimov, it's the median. What is the power? It's the median. What is the power of the median? I cannot hear you. 1/2. Because it's the median. So 50% of the entries fall here and 50% here. So for the expectation, I divide by the power, which is 0.5. So my real expected significance taking into account the power is 3.4%. This is fantastic. I go for it. Now, let's look at the real observation. Let's look at the real observation that gives me 5% p-value. This area here. This is the observation here. This is 5%. Now, the power, which is this area here, is 68%. So even though I would be tempted to exclude the Higgs with this analysis. I would say, wait a second, the power is 68%, so the CLS, or P prime, is 7.3%, so the confidence level is not 95, but 92.7%, 100 minus this. So no exclusion. Now I can ask myself, where should this observation be in order to exclude the signal at 95% confidence level? So I should find a place here where the p-value divided by the power is 5%. And here I find it. I should move here. The blue area here is, in this place here, is 2.94%. The power, which is this area here, the dashed line all the way to infinity, is 58.8%. And if you calculate the ratio between the two, you'll get that it's 5%. So this is the game. This was done with a luminosity of 20,000. Now let's increase the luminosity to 40,000. When I increase the luminosity to 40,000, they are more separated. So you see, what happens is that now the power is 91%. So the 5% is only spoiled to 5.5%. So the confidence level goes down from 94.5%, from 95 to 94.5%. So in order to really get 5%, all I need is to have a measurement a little bit close to it. So when the luminosity is high, the CLS is actually, the p-value is identical to the CLS. As the luminosity increases and increases, the power will go towards 100%, and you won't have a problem with your p-value. Now let's decrease the luminosity. Let's decrease the luminosity to 10,000. You were at 20,000 to 10,000. In this case, the 5%, the power becomes 43%, decreasing. The 5% goes to 11%. Very bad. Now let's go to low luminosity. I go to low luminosity, something crazy happens. Suddenly, they are very close to each other. I cannot really separate between the signal plus background hypothesis and the background only hypothesis, right? This is the signal plus background, and this is background only, and I cannot really separate. So it doesn't even look like it. It looks like a modified chi-square, something like this. And it should, because when the signal is, when the luminosity is low, the signal and the plus background equals about the background, so it's the same distribution, more or less. So if I was tempted to exclude the Higgs with a p-value of 5% here, the power is only 20% here. So the p prime becomes 25%, and the confidence level drops from 95 to 75%. There's nothing I can do, and that's the way CLS works. Now I can ask myself, even with this, is there a way to have an exclusion? Suppose that I get a measurement somewhere here. So indeed, there is a place. If you go somewhere very, very far here, close to 4 sigma, then your p prime becomes if you go to this place here, your p prime becomes actually 6.810 to the minus 5. And the power is 0.136%. This is crazy. So your CLS becomes actually 5%. But look, this is crazy. This is crazy. You won't believe it because the p-value for the alternative hypothesis is also so low. You won't believe this thing. You could do it, but you won't believe this thing. So it's hard to digest an observation with the power of less than 5%. I mean, the power is not at least something like 50%. You don't believe anything you're doing. This is my opinion. But it's nice that you can draft the asymptotics to actually calculate for you easily the p prime, the CLS. Look, p prime u is p mu over 1 minus p0. We have all the formulas for that. And all we have to do is to scan mu and find mu up given by all the mu that 1 minus phi of square root of q mu observed, or phi of square root of q mu Asimov minus square root of q mu observed is 5%. That's very easy to do. So the asymptotics comes to our rescue even here. This is not in our paper, but we derived it later. But asymptotics comes to our rescue even when it comes to the CLS, and we actually can do it. So time doesn't permit to give examples. You can look at them yourself. Examples include the... Actually, I want to show only one thing. When we did the discovery, when we started to look for the Higgs, look, the p-value at 125 went down. So we were very happy. We had 3 sigma here, and it was November 2011, and there was a press conference here, December 2011. You remember I mean, you're young, but there was a press conference here. And then, as the journalists went, and then we suddenly discovered that it disappeared. So things flashed, and then it came again, okay? Things happen. And then, who knows, you know. And okay, you can look at all these things. These are examples. You should be able now to read everything and understand everything. And this is a real spin example like I did last time, and you should be able to understand everything. More magic tomorrow. Okay, thank you very much.